Hey everyone, and welcome back to this class, Modern Deep Learning in Python, Deep Learning in Python Part 2. In this lecture, we are going to compare the Atom optimizer in code versus RMS prop with momentum. If you don't want to code this yourself, although I strongly recommend you do, the relevant file in the course repo is atom.py. So most of this code is just copy-paste from our previous RMS prop script. So I'm going to focus only on the important parts. This script specifically is going to compare Atom and RMS prop with momentum. I've added momentum to RMS prop in order to make it a more fair comparison, since Atom also incorporates momentum. The main outline of the code is still the same. We load in the data, initialize some weights, and go through the training loop using the algorithm we are interested in. So first up is Atom. So I initialize the first and second moments to be all zeros. Note that while they could be initialized to an array of zeros, it's just as valid to initialize them as scalar zeros, since NumPy knows how to automatically broadcast a scalar when you add it to an array. Next, we initialize the Atom parameters. We're going to use these same parameters for both Atom and RMS prop. So the learning rate is 10 to the minus 3, beta 1, which corresponds to the decay rate for the first moment, which can also be thought of as momentum, is 0.9. Beta, which is like the RMS prop cache decay rate, is 0.999, and epsilon is 10 to the minus 8. Next, we have the training loop. So we start out by calculating the gradients for each array. I've prefixed these with G for clarity. Next, we calculate the updates for M. This is the exponentially smooth average of the gradients. Next, we calculate the updates for V. This is the exponentially smooth average of the square of the gradients. Next, we do the bias correction step. By convention, the first time index will be 1. Next, we update T. And finally, we apply the Atom update equations to the parameters W1, B1, W2, and B2. Everything else here is boilerplate code where we keep track of the costs and errors so we can plot them later. Next, we have RMS prop with momentum. So you can see here that the RMS prop parameters are the same as the Atom parameters. Specifically, the learning rate is still 10 to the minus 3. The momentum term, which corresponds to beta 1, is 0.9. The cache decay rate, which corresponds to beta 2, is 0.999. And epsilon is 10 to the minus 8. Next, we initialize the cache. So I'm going with the one variation here, which is different from how Keras does it, but the same as how TensorFlow does it. And this is in order to make the updates more comparable with Atom. We need to do this because RMS prop does not have bias correction. Next, we initialize the velocity terms to 0. These will not be bias corrected, so we'll see if it makes a difference. Next, we have the updates. So the general form is we're going to do everything we did for RMS prop, but just add momentum to it at the end. So we first calculate the gradient, and then we calculate the cache update. Next, we use this variation on momentum, which I mentioned in the Atom lecture. So instead of weighting just the previous velocity, we weight the change that we would have made by 1 minus mu. So instead of just having mu times dw2, we have mu times dw2, and then we add another constant, 1 minus mu, to the learning rate times gradient update that we normally would have done. There are, of course, multiple ways to implement momentum, but I think this way leads to the most fair comparison between Atom and RMS prop. After this, there is again some more boilerplate code to save the cost and error, and then we plot the results. So let's run this and see what we get. So we can see that RMS prop and atom actually end up very close to one another. This makes sense because atom is basically RMS prop with momentum added to it. The big difference is that atom adds the bias correction step. We can see that this makes a big difference at the very beginning, but the influence of this bias quickly goes away. You observe the same effect if you run just a low-pass filter on a random signal. You'd see that the output is initially biased towards 0, but the bias goes away pretty quickly.